hand. Touch the table in front of you. Take a breath of air. It feels solid. It feels permanent. You trust the matter that makes up your reality because it has been stable for billions of years. But that stability is an illusion. Everything you can see, from the stars in the sky to the neurons in your brain, is made of normal matter. At the subatomic level, this means protons and neutrons. Inside those, you find up quarks and down quarks. These particles are held together by the strong nuclear force. But mostly, an atom is just empty space and energy. It is a delicate arrangement, and like all delicate things, it can be crushed. To see how matter breaks, we have to travel to the universe's hydraulic press. The neutron star. When a massive star dies, its core collapses under its own weight. The gravity is so intense that it breaks the laws of atomic physics. Electrons are smashed into protons. They merge to become neutrons. The empty space inside the atom is squeezed out. Imagine taking all the humans on Earth, 8 billion people, and crushing them into the size of a sugar cube. That is the density we are talking about. The star is no longer made of atoms. It is a corpse made of crushed nuclear material. What is left behind is an object that defies comprehension. A neutron star is essentially one giant atomic nucleus the size of a city. It is a sphere of neutrons packed shoulder to shoulder, spinning hundreds of times a second. If you could take a single teaspoon of this material and bring it to Earth, it would weigh 1 billion tons. If you dropped that teaspoon, it wouldn't just sit on the floor. It would punch through the Earth's crust like a bullet through tissue paper. But even this is not the limit. We understand the surface of these stars. It is a crust of iron. We understand the mantle. It is a superfluid of neutrons. But the center, the dead center of the star, that is a mystery. Deep in the core, the pressure rises to levels we cannot reproduce in any laboratory. It squeezes the neutrons so hard that they start to overlap. The boundaries between particles blur. The question that haunts physicists is, do the neutrons break? The answer is likely yes. Under this crushing weight, the neutrons, which are basically bags holding quarks, dissolve. The bag rips open. The up and down quarks spill out. They are no longer confined inside particles. They become a free-flowing liquid. This is called quark matter, or quark soup. But in this extreme environment, something strange happens. The energy is so high that a new guest arrives at the party. A third type of quark appears. It is heavier, it is stranger, and it might be the end of everything. Inside the crushed core of the star, the physics changes. Normal matter is built from 2 specific ingredients: up quarks and down quarks. They are light, they are stable. They are the bricks of the universe. But under extreme pressure, some of the down quarks are squeezed so hard they transform. They become strange quarks. Strange quarks are much heavier and usually decay instantly in our world. But inside the neutron star, the pressure keeps them alive. The core becomes a mixture of up-down and strange quarks. This is where the nightmare begins. In the 1980s, physicists Arnold Bodmer and Edward Witten proposed a terrifying hypothesis. They suggested that this mixture, strange matter, might be more stable than normal matter. In physics, stable means perfect. It means the particles are happier, tighter, and require less energy to exist. If this hypothesis is true, strange matter is the ideal form of existence. Protons and neutrons are just cheap, unstable imitations. To understand the danger we have, to look at energy levels. Imagine a ball sitting on a high ledge. It stays there because of friction, but it has potential energy. It wants to be on the ground. The ground is the true ground state. The Bodmer-Witten hypothesis suggests that we are the ball on the ledge. Normal matter has high potential energy. Strange matter is the ground. The universe is constantly trying to find the lowest energy state. It wants to fall. This concept is called metastability. We are not truly stable. We are just stable enough for now. We are living under tension. Normally there is an energy barrier that keeps us from collapsing into strange matter. It's like a wall on the edge of the ledge that keeps the ball from rolling off. But if you remove that wall, the fall is inevitable. And this is the horror of strange matter. It is infectious. If a piece of strange matter touches a piece of normal matter, it acts like a seed. The normal matter sees the lower energy state of the strange matter and wants to join it. The energy barrier dissolves. The protons and neutrons in the normal matter collapse. Their quarks are sucked in and converted into strange quarks. It is the nuclear version of the Midas touch. Anything it touches turns into itself. And once the process starts, there is no known force in the universe that can stop it. If this matter only existed inside neutron stars, we would be safe. The gravity there is a prison, but sometimes pieces break off. These fragments are called strangelets. They can be huge or they can be microscopic. A single strangelet could be the size of a grain of sand, yet weigh as much as an aircraft carrier. Because it is held together by its own nuclear gravity, it doesn't need external pressure to survive. It remains stable even in the cold vacuum of space. It is a subatomic landmine, a perfect, indestructible droplet of death waiting for something to touch it. How do they escape the star violence? We know that neutron stars collide. We call this a kilonovae. When these titans smash together, they don't just create black holes, they spray their insides across the galaxy. Tons of neutron-rich matter are ejected into the void. Most of it decays into gold and platinum. But if the core contained strange matter, then strangelets are thrown out too. They become cosmic shrapnel drifting silently through the dark. This leads to a terrifying possibility. Space is vast. The odds of hitting anything are low. But over billions of years, the galaxy has been filled with the debris of millions of dead stars. A single strangelet, perhaps no bigger than a marble, could be drifting through our solar system right now. It would be invisible to radar. It gives off no heat. It reflects no light. It acts like a heavy, dark bullet. And unlike an asteroid, we wouldn't see it coming until it was already here. What happens if it hits Earth? An asteroid burns up in the atmosphere because of friction. But a strangelet is too heavy and too dense to care about air resistance. It would punch through the atmosphere like a needle through fog. It wouldn't slow down. But as it moves, it touches atoms. Nitrogen. Oxygen. This is first contact. The moment a nucleus of an oxygen atom touches the surface of the strangelet, the reaction begins. The oxygen doesn't bounce off, it is absorbed. This is not a chemical reaction, it is a nuclear collapse. The protons and neutrons in the air atoms encounter the strangelet. They realize that the energy state inside the strangelet is lower than their own. Nature always seeks the lowest energy, so the barriers dissolve. The quarks inside the air atoms flow into the strangelet and are instantly converted into strange quarks. The air atom ceases to exist. It becomes part of the strangelet. The strangelet gets slightly bigger, it gets slightly hungrier, and it releases a burst of energy as heat. The spark has been lit. Once the reaction starts, it creates a feedback loop from hell. The conversion releases massive amounts of energy as heat. This heat melts the rock around the strangelet, making it easier for new atoms to flow into the trap. The strangelet gets heavy. Gravity pulls it down. It sinks through the crust. It eats through the mantle. It falls all the way to the Earth's core, consuming matter every inch of the way. It grows exponentially. First, it is the size of an atom, then a marble, then a basketball. Inside the Earth, a fire has been lit that water cannot put out. This is not an explosion. It is a collapse. Strange matter is billions of times denser than rock. As the Earth is converted, it doesn't just burn, it shrinks. The crust would buckle and fall into the magma ocean. The atmosphere would be sucked down into the vortex. The entire planet would be consumed in a matter of hours. It would glow brighter than the sun as the nuclear bonds snap. And then, the Earth would vanish. What is left behind? In the place where our world used to be, there would be a sphere of strange matter, roughly the size of a bowling ball or an airport. But it would still contain the entire mass of the Earth. The gravity remains exactly the same. Yeah, The moon would continue to orbit this tiny, invisible rock as if nothing happened. The satellites would still circle it, but the biology, the history, the oceans, and the people would be compressed into a dense, hot metallic soup. We would finally be stable. Now, take a breath. Why hasn't this happened yet? The universe gives us a safety guarantee: the moon. For billions of years, the moon has been bombarded by high-energy cosmic rays. These impacts are powerful enough to create strangelets naturally. If strange matter were truly contagious and stable, a single impact should have converted the moon into a strange star eons ago. The fact that the moon is still made of gray rock tells us that strangelets are either impossible to make or they are unstable and fall apart before they can grow. The universe has been testing this theory for us, and so far we have passed. This theory leaves us with a profound realization. We often strive for perfection. We want stability, but in physics, stability is death. If matter were perfect, it would be a cold, dense lump of strange matter. We exist only because the universe is imperfect. We are metastable. We are fragile. We are energetic. It is the tension, the refusal of matter to settle down, that allows life to exist. We should be grateful that we are flawed, because to be perfect is to be nothing at all.